All right, let's work through the angular kinematics worksheet. And I'm just going to jump right into it. We have a 2 meter wheel, and that is the diameter of it. That's the tricky part of this question is that the radius or the diameter? And if you did this with radius, that's fine, as long as your process is the same. And I'll show you what the answer would be, what the answer should be had you used radius in this problem at the end. But I'm going to assume it's the diameter, which means my radius is 1 meter. And we have it's rotating clockwise at a speed of 10 times per second, so it's going this way. And again, just like I said in the notes, clockwise we're going to treat as negative, counterclockwise we treat as positive, just like we would treat right as positive, left as negative, up as positive, down as negative. You can switch them. You can call left positive and right negative, but it's going against convention, and I'm going to be sticking with convention so that way you can follow me and hopefully I'll feel a little more consistent to you. But we have a speed of 10 times per second. So it's going around 10 times per second. And this is something you just kind of have to get used to the lingo. If it's going around 10 times per second, that means it's doing 10 revolutions per second. So the angular velocity is 10 rev per second. And as always, I'm converting into what we want, and our angular velocity should always be in radians per second. So I'm going to do that right from the jump. I know that 1 rev is equal to 2 pi radians. And we can cancel rev, and we're left with radians. So 10 times 2 pi is 20 pi radians per second. Or, 20 pi radians per second. And I want to clarify, radian is a unit, and yes, that is equal to the size of 1 radius, but it is still a unit. And also you have 2 options when you're doing rotational. You can leave it in terms of pi, and you can just carry 20 pi through, and a lot of times your answers will have pi in them. So it's good to get used to doing it both that way and actually doing the calculation, but we know pi is just 3.14, so it's 20 times 3.14 radians per second, or 62.8 radians per second. In fact, that's our answer to A, rate from the jump. What is the angular speed? 62.8 radians per second. And I should clarify in here, in rads per second. And B, what is the angular displacement? So we are looking for theta, and again, these equations are identical to your kinematic equations, but just replacing it. So I'm going to go with theta equals, we have constant velocity, right? It's a constant speed, which means acceleration is 0, or rather, angular acceleration equals 0. Which I think means we can use the second equation. Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And if you forget from class, position, velocity, acceleration, just like in your kinematics equation. If you forget what they are, just look at your original equation. And they're exactly what they seem like. All right, so now let's plug it in, or plug in our values. I'm going to assume that the initial position was 0 and the acceleration is 0, so the first term and third term disappear. So theta is just omega naught t. We know the angular velocity is 62.8 radians per second. And we know that the time is 3 seconds. And our angular displacement is going to be 62.8 times 3, which is 188 radians. I hope. I haven't checked my answers, so if I made a mistake, there's a possibility that or if our answers disagree, there's a possibility that I'm the one that made the mistake, and if that's the case, just let me know. Now for part C, this is where the assumption of what is the radius, is it 2 meters or is it 1 meter, will make a difference. I'm going to assume it's 1 meter, but I'll show you what the answer is if you assume 2 meters. And again, go with the Vromega equation. Velocity equals radius times omega. And I'm going to remind you from what I said in class, but theta equals, x equals r theta, and a equals r alpha. So basically multiplying the radius times the position, the velocity, or the acceleration will get you the linear position, velocity, or acceleration, which makes sense. Bigger velocity times the same angular rotation speed gives you a bigger linear velocity. That's why you want to sit towards the outside of a Ferris wheel. So plugging it in, we know the radius is 1 meter times the angular velocity, which we calculated to be 62.8 radians per second. And that's going to give us 62.8 meters per second. And if you had a radius of 2, then you would just multiply this answer by 2, and you would have gotten 377 meters per second instead. And the reason we can do that is 1 meter is equal to 1 radius, or 1 radian, and radian will cancel out, and you're left with meters per second. All right, 2, 50 centimeter diameter wheel, which I don't ever care about diameter, so the radius is 0.25 meters. Radius equals 0.25 meters. And the wheel rotates through 25 radians, so we know the angular displacement, or final position minus initial, well, let's just put initial position as 0. Final position is 25 rads. And I'm going to put units just because this is new and early. What distance will the treads on the outside of the tire move? So we're trying to figure this out. Oh my goodness. By the way, in the previous question, I forgot to put negative 10 radians. So all of these answers should have been negative. Negative 188. This would still be 62.8 because the velocity is positive. They didn't say if we were at the top or at the bottom or the side, but the speed is 62.8 meters per second. But the angular displacement was negative 188 radians, and the angular velocity was negative 62.8 radians per second. I'm sorry for that. Coming back to number 2, the initial velocity, it doesn't say, but this question implies that it's going this distance, and I'm going to assume the angular acceleration is 0 because it's a wheel rotating. We can pretty much assume it's going constant velocity, I think. I don't think we'll need to, though. What distance will the treads on the outside of the tire move? Maybe it's not fair to assume there's no acceleration. Maybe it's just because this equation doesn't require it. But we're trying to find the linear distance that the treads will move, and that's equal to r times theta. We know r, we know theta. All you have to do is multiply them. So 25 times 0.25 should give you 6.25 meters. Done. Ooh, in a box. Done. 2. 2b. 2b. No, this is 3 because the next one's 4. I did fix that in the updated document, but I'm going to work through this one that you guys have. Find the angular velocity of a wheel. So we're trying to find the angular velocity that rotates at 120 RPM. Oh, so we are given the angular velocity. 120 rotations or revolutions per minute. So this is a conversion problem. I'm going to convert minutes to seconds. So with conversion problems, especially with top and bottom conversions where you have to convert them both, I am going to show my conversion factors using the train track method. Mark where you start number 1. Write down the units that you want to end with number 2. We want to get radians per second. And then fill in your conversion factors. We know 1 minute is 60 seconds. And we know 1 rev is equal to 2 pi radians. And you can either convert the the top or the bottom first. It doesn't matter. I'm going to go with the bottom. Minutes going to have to go in the numerator to cancel it out, and we can go from minutes to seconds, and then just fill in the gaps. How many minutes? 1. How many seconds? 60. And now we've canceled out minutes, and we're left with seconds in the denominator. So we're set for the denominator. But now we have to get rid of revolutions, so rev has to go in the denominator, so they will cancel, and we can go from revs to radians. 1 rev is equal to 2 pi, or if you want, you can just put in 6.28 because that's equal to 2 pi. And that's actually what I'm going to do because I hate pi. So 120 divided by 60 times 6.28 is equal to 12.6 radians per second. And what's the tangential velocity if the radius is 0.25 meters? Oof, I'm getting color doused. Radius equals 0.25 meters. And we've already hopefully memorized the omega equation. We know the radius is 0.25 times the omega, which is 12.6. So basically 12.6 divided by 4 will give you your velocity, which will be about 4-ish. 3.15. Oh yeah, I divided by 3. 3.15 meters per second. Because I will work through that. I don't want to be sloppy. 0.25 meters is equal to 1 radian, or 1 radius, and this was in radians per second. So radians will cancel, and we're left with meters per second. And that should be your tangential or linear velocity. Find the angular velocity of a 40 centimeter radius wheel. So radius is 0.4 meters. I'm always converting that to meters. If I see centimeters, I'm getting rid of it immediately. 0.4 meters. That's moving at 20 meters per second. So that's our linear velocity because it's in meters per second. Always use your units as a hint. Always, always, always. How many times will this wheel rotate in 5 seconds? So we're trying to find the displacement, but we want it in revs. But we're going to find it in radians first and then convert it to revolutions. I said how many times will it rotate? That's why I knew how many revs. So now, if we're trying to find theta, it's moving at 20 meters per second, which means it's not speeding up, it's not slowing down, so we can assume, based on that wording, acceleration is 0. I think that's the trickiest part of this question. So this looks like the second equation, but I'm going to jump and convert this into radians per second using the omega equation. Or rather, angular velocity equals the velocity over radius, which is 20 meters per second divided by 0.4 meters per radian, or per radius, and 20 divided by 0.4 is 50 radians per second. So now that we have that, it looks like we can jump into the second equation. And if you're not sure, just try all 3 equations and see what sticks. But after enough times, you'll get used to seeing, okay, acceleration is 0. We're trying to find theta. That leads me to believe we're looking at the second equation. And I think after kinematics, you've probably gotten a little bit better at it at this point in the year too. But acceleration is 0. Initial position is 0. So theta equals omega naught t, and we're given a time of 5 seconds. I forgot to put that in my list. That was very lazy of me. So theta equals omega naught t, or we can solve this equation for, oh no, we are trying to solve for theta. Perfect. So 50 radians per second times time, which is 5 seconds. So that's going to give us 250 radians total. And now we can convert this to revolutions. Well, we know 2 pi radians is equal to 1 rev. Ooh, that's way too big of a line. So 250 over 6.28 is 39.8. By the way, if you did your math in terms and left pi as part of your answers, that's fine. Just to check yourself, plug in, if you get, I guess this would be 125 over pi radians. I'm not going to do that for every problem, but all you have to do is plug in 125 over 3.14 and see if you get the same answer as me. But you can always check yourself just by plugging in pi. But I'm not going to do the problems twice. That seems very redundant. All right, 5. We have a saw blade spinning at 2,000 RPM. RPM is revs per min, and that is an angular velocity, but it's a clunky unit. 2,000 rev per min. And if you guys want a more detailed explanation of how I'm going to convert this, you can go back to question number 3. But I'm just going to crank through it. 1 rev is equal to 2 pi radians. And I'm actually just going to put in 6.28. And 1 minute is equal to 60 seconds. And that'll leave us with radians per second because rev will cancel and min will cancel. And 2,000 times 6.28 divided by 60 equals 209.3 radians per second. And I know I always use 3 significant figures, but this time I left a 4th on there. I try not to round until the end, at least not round too badly. And I think that's good practice. You don't have to do that. You could have just said 209, assuming that is the right answer. I didn't make a mistake. And actually, that's our answer to A. So A is done. B, how many radians will it spin in time equals 2 seconds? So T equals 2. I'm going to add that to my list, even though I made very little list. And that is immediately leading me toward equation number 2. Again, because of the lingo, it is spinning at. That means constant velocity. Now, you might see when it is spinning at. That would mean it's probably speeding up or slowing down. But if they just say it is spinning at that, then you can assume acceleration is 0. The initial position we can assume is 0. And at this point, you just plug in omega naught t. So theta is 209.3 radians per second times the time, which is 2 seconds. So basically, you multiply your previous answer by 2, and you should get 419 radians. I hope. And C is how fast are the blade tips moving. Ooh, we are given the radius. Ooh, that's diameter. That's diameter. Cut it in half. So the radius equals 0.15 meters. And I'm going to put that over in my list just so I have all of that information in one handy-dandy, easy-to-look location. We're trying to find V, how fast. V is vromega. So 0.15 times our angular velocity, which we solved for in part A, 209.3. Times 0.15, 31.4, hopefully, meters per second. And if you want to know how I got from radians per second to meters per second in terms of units, look at the end of number 3. I did walk through it there. 6, automobile tire of radius. Ooh, they even gave it to us in meters. Good for them. Radius equals 0.356 meters. And you know what? Let's spice things up a little bit. Let's go to, I think I've already done green. Maybe I haven't. No, I haven't. On a car traveling 60 miles per hour. Gross. Has an angular velocity of 75.4 radians per second. Thank you for giving us that. That's so much better. 75.4 radians per second. And it slows down, so there is an acceleration to a final velocity. So this was our initial velocity. This is our final velocity, 18.7 rads per second, or radians per second. And we were given time. Time equals 10 seconds. And they want us to find acceleration. Again, we're given... Ooh, I don't think we know theta, which rules out the second equation because we would have two unknowns. V equals V naught plus AT. V naught T. We can use the first equation to solve for acceleration. Yeah. Omega equals omega naught plus alpha T. 18.7 equals 75.4 plus alpha times 10. And if you wanted, you could have rearranged this equation. Omega minus omega naught over T equals alpha. And then it would be 18.7 minus 75.4 over 10 equals alpha. So alpha equals negative 5.67 radians per second divided by seconds, or radians per second. Just like acceleration is meters per second, this is radians per second. I know we went over that in the notes, but I'm going to reiterate it here. 7, a centrifuge. Ooh, I did do 6, 7, 8 on this. Yeah, negative 5.67. That is the answer I got before. I don't know where I did my other work, but 6 is the same answer I got in school. All right, so we have a centrifuge going around. And it reaches a final angular velocity of 30,000 revs per min. And again, every time I see it, I'm immediately going to convert it. 1 rev is equal to 6.28 radians. Reference number 3, if you want to see me work through this more detailed. But 1 minute is equal to 60 seconds. Revs cancel. We're left with radians per second. That's what we want. So 30,000 times 6.28 divided by 60 is 3,140 is our final angular velocity, radians per second. By the way, to go from revs per minute to radians per second, you're always going to do this step, which is always going to be 6.28 divided by 60. So, I hate to tell you this, but this is always going to be equal to 0.104. If you can somehow remember 104 or 104.7, maybe that's your favorite radio station, 104.7. I think that is a country radio station in our town. I think that works out splendidly. So if we're trying to convert revolutions per minute to radians per second, you're riding down the road at this many revs per min. You multiply it by 104.7 or 0.1047, basically divide it by 10, which, goodness gracious, that looks like it's divided by 10. It's pretty darn close. So 104.7. That might save you a ton of time. I wouldn't recommend it, but I actually might start doing that because it's fun for me. And we're given a time of 5 seconds. And we're trying to find the angular acceleration. Starts from rest, so we know the initial angular velocity is 0. And this looks like that first equation. It definitely is. Omega equals omega naught plus alpha t. And I'm actually going to rearrange this for alpha. So omega minus omega naught, I'm going to subtract this from both sides, equals alpha t. And then divide both sides by t. And then alpha equals the change in velocity over time. That's what acceleration is, right? Change in velocity divided by time. Plug them in. Bum, bum, dun, 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 dun. Oh, that's phenomenal. Oh, divide by 5, not 10. And you should get 628 radians per second per second. Is that what they wanted? I'm going to check the question because I wasn't really paying attention. Angular acceleration in radians per second per second. Oh, goodness gracious. Me, oh my. That's not what I... Oh, that is what I got. Good. So 628 radians per second. 8. Engine slows from this. This is the initial velocity. To this. This is the final velocity in this much time. What is the theta of this engine during the time period? We're given the initial velocity. But we're not given acceleration, so we can't use the second equation. And the third equation, we're also not given the acceleration. So we're going to have to double equation this. We need to solve for acceleration before we can use the others. So I'm actually going to go to the first equation to solve for acceleration and then plug it in. And again, I'm going to rearrange this. Acceleration is change in velocity over time. Or... oh, they're all in RPM. But you know what? Let's go wild 1047. Let's have some fun with this. So let's do... okay, which one's our final? This is our final. 500 RPM times 0.1047. So our final velocity should be 52.35. That's fun. That's very fun. Radians per second. And let's do the same for the initial. There's no way I should be doing this in a video. 3,000. And if you're not comfortable, please don't do this. But if you are comfortable and you're like, you know what? I get it, dude. Just show me the shortcuts. Then go for it. You should judge for yourself whether you feel comfortable with this or not. I'm definitely going to remember it, especially because it's a country radio station. I don't like country, but that doesn't matter now, does it? So now we have those. We know the time is a time of 4 seconds. And then we can plug them in. Final minus initial, which should be 52.35. And I know that it's slowing down, which means that this should come out to be a negative answer. And looking at this, yeah, that's going to come out to be negative. Always kind of be paying attention to those little tricks while you're working. Like, think about what the answer should be conceptually and see if your answer agrees with it. If it doesn't, go back and check your work along the way. So you should get negative 65.4 radians per second. And now that we have acceleration, all of the equations are fair game, but I'm still going with this one. And I'm actually going to bring this to this side. Theta minus theta naught equals omega naught t plus 1/2 alpha t squared, because they asked us to solve for the angular displacement. And final minus initial is the change in, or the displacement. And you didn't need to know that, but that's something I don't highlight enough in class because I always feel rushed. And for those of you taking the time to watch the video, I figured I'd try to show you something that I should say. The initial velocity is 314 times a time of 4 plus 1/2 times negative 65.4 times 16, or rather 4 squared. Don't forget your squared. Don't forget your squared. That's the biggest mistake people will make. And then you plug it in and you should get 733 radians. And they wanted angular displacement, and we're done. Good. If you did that, great. Thank you for watching. I hope you enjoyed it. I'm going to do the challenge question. And if you want to come along for the ride and get a bit of a head start on the next lesson, you're welcome to. Let's jump into it. The moment of inertia, which is the rotational equivalent of mass. And it depends on the shape of it And this saw blade is a solid cylinder. For all intents and purposes, it's a very thin cylinder, but it is a cylinder nonetheless. And I'll draw that down here. Where the equation for a solid disk, or rather to calculate the moment of inertia of a solid disk, is 1/2, and actually I'm going to put the subscript on there. This equation is different for all shapes, but for a disk or a cylinder, it's 1/2 mr squared. And all of the equations are some sort of iteration of mr squared. So a hollow hoop, because all of the mass is located at the max radius, is just 1 mr squared. But because this mass is averaged towards the middle and the outside, that's where that 1/2 comes from. And hopefully that'll help you remember the equations a little bit more easily. But we're given the diameter, which means the radius is 0.15 meters. And we know the mass is, that's in grams. And remember, 1 kilo is 1,000, so 200 grams is 200,000th of a kilogram, or 0.2 kg, basically divided by 1,000. So for part A, 1/2 times the mass of 0.2 times the radius of 0.15. Don't forget to square it. 0.1 times 0.15 squared is... my calculator is spitting out 2.25 times 10 to the negative third kilogram meter squared, kilogram square meters. But if you don't like, you should get comfortable with this, by the way. But if you don't like that, that's equal to, hey, move the decimal to the left 3 spots. So 0.00225 kilogram meter squareds. So that's your moment of inertia, or rather the rotational mass of it, if you want to think about it that way. And remember, just like mass, it's how hard something is to shake, right? So if you were to shake a doll that's made of cotton, it's going to be relatively easy to shake. But if you fill that cotton with lead and you're shaking it then you try to shake it, it's going to be much harder to shake. Linearly, it's called mass. Well, the rotational equivalent is, hey, how hard is this sucker going to be to turn? And the bigger the moment of inertia, the harder it will be to turn. Which means think about turning a heavy steering wheel. It's like, oh my goodness, that was hard. It has a big moment of inertia. It's hard to turn. The teapots, if you've ever been to a theme park, those have a big moment of inertia because they have a lot of mass located towards the outside. The more mass is towards the outside, the harder something is to rotate. Which, that's your figure skater thing, right? If your arms are out, you're harder to spin, but as soon as you pull your arms in, who goodness gracious do you start to fly? All right, B, because I haven't looked at that yet, or rather 2. 2B, not 2B, whatever. How would that answer be different if it were a hollow saw? Well, we already said this. The moment of inertia of a hoop, because that is a hoop shape, is 1 mr squared. Well, a hollow saw with identical dimensions, that means the mass is the same. So 1 times the mass, which is 0.2, times the radius, which is 0.15 squared. So it would just be that answer, but times 2, which we should have seen from this equation going to this equation. All we're doing is doubling it. So that would be 0.0045 kilogram meter squared. I'm going to plug that in just because I don't want to get it wrong. That is right. All right, 3. What about a solid sphere? And again, you're already seeing, hey, this is the same thing. I'm actually going to have to look up the moment of inertia for a solid sphere because I don't have that memorized. So I'll be right back. All right, so I actually looked up the equation for both 3 and 4. They said a solid sphere versus a hollow sphere. I should have asked where you thought which one would have more moment of inertia. Well, of course it's going to be the hollow one, or what we call a spherical shell, because the mass is located at a bigger radius. Again, figure skater should be your main thought. The further out the mass is located, the bigger the moment of inertia and the harder it's going to be to turn. And all of these end in mr squared. All you're doing is changing the coefficient. Basically, what percentage of how far out is the weight distributed. This one, in a solid sphere, the weight is about 2/5 the way out. And in a spherical shell, it's about 2/3. So then we can just plug it in. 2/5 times 0.2 times 0.15 squared. And that's going to be 2/5 times 0.2 times 0.15 squared. Oh, goodness gracious me, oh my. 0.0018 kilogram meter squared, which is the least we've had so far. And a spherical shell, this has to be more because the weight is more distributed towards the outside. So 2/3. I guess I could have just left this equation in my calculator and changed the coefficient. But this is going to be 0.003 kilogram meter squareds. But I hope you got something out of that. If you made it all the way to the end, shablagoo. And also, did you hear the joke about butter? I'm sorry, it's just a rumor. I probably shouldn't spread it. Have a great night. I hope you enjoyed this, and I'll see you in the next one. Bye.